All right, let's just jump right in because this one is a real mind bender. We all learn that gravity is a force of attraction, right? Matter pulls on matter. But what if that's only half the story? What if the default state of the universe, that huge black emptiness between galaxies, is actually pushing things apart? There's a new paper out that seriously challenges some of our most basic ideas about how space-time works. Now, this isn't some flash-in-the-pan idea. This comes from almost 2 decades of work by an independent theorist named Gerald Welch. So what we're talking about here is a really deep, long-term project aimed at rethinking the universe from the ground up. So here's our game plan. First, we'll talk about what we think empty space is. Then we'll get into this wild new idea of a repulsive baseline. After that, we'll see how the gravity we know and love could actually pop out of that. And, this is the best part, how we can test it using these giant cosmic voids. And finally, we'll see why this is a real, testable, and falsifiable piece of science. Okay, let's start with ground zero. The picture that's in all the textbooks. Just take a second and think about that. I mean, really think about it. If you could wave a magic wand and make every star, every planet, all the dust and gas just vanish, what would be left? What is the actual fundamental nature of empty? Well, the standard answer, the one we've been working with for over a century, is that empty space is basically a blank canvas. It's called Minkowski space. It's just this flat, neutral, totally inert background. Gravity isn't a property of space itself. It's something that matter adds to the system, like an actor walking onto an empty stage. And now, here is where we get the big twist. This paper suggests a whole new way of looking at things, kind of like a Copernican revolution for gravity itself. This slide just flips the whole thing on its head. The standard view, baseline is flat, gravity is attractive. The proposed view? No, the baseline is repulsive, and the attraction we feel is just a weird little local exception. It totally reframes the question. Is the 95% of the universe that's empty void the strange part? Or are we, living in our crowded little 5%, the real anomaly? And when you look at the actual numbers, it's pretty staggering. By volume, the universe is overwhelmingly empty space. About 90% of it is these vast, underdense cosmic voids. We live in that tiny sliver of structure. So you gotta ask, why on earth should we assume that our little corner of the cosmos represents what's normal? So this leads us to the core idea of the whole paper. It's a formal postulate, but what it's really saying is simple. If you could get to a place that is truly perfectly empty, as the energy density goes to zero, the true nature of space-time would reveal itself. And that nature is repulsive. Put simply, empty space doesn't want to just sit there. It wants to expand. Okay, you're probably thinking, if the baseline is repulsive, why am I not floating off my chair right now? Why do apples fall down? That is the million-dollar question. How do we get our familiar attractive gravity? And the answer is a really cool concept, suppression. The idea here is that attractive gravity isn't something that's added to spacetime. Nope. Instead, matter and energy actively work against the vacuum's natural repulsion. They cancel it out. And what we experience as gravity is just what's left over from that fight. It's the net effect.
There's a fantastic analogy for this. Picture space-time as a spring that always wants to be open. That's your repulsive baseline. Now imagine a latch that can hold that spring closed. Matter and energy, that's the latch. Where we are, in a galaxy, in a solar system, there's a ton of matter, so the latch is strong and it's holding that spring tightly shut. It's suppressing the repulsion. And that suppression is what we feel as gravity.
Look, a cool idea is one thing, but for it to be science, you have to be able to test it. So how in the world could we prove or disprove something this fundamental? Well, you go where the idea should be most obvious. You look where there's the least amount of matter doing any suppressing. And that means we have to look into the hearts of those giant cosmic voids. If space really is repulsive at its core, then in those incredibly empty regions, that repulsion should be showing itself. It's gotta be there. And this isn't just a vague prediction. It's incredibly specific. The theory says that as light from a distant galaxy passes a void, it should get bent away from the void center a tiny bit more than our standard models say it should. This effect, which they call epsilon void, has to be a positive number. Not only that, but the signal should get stronger for voids that are bigger or emptier. They even predict the exact shape of the signal as you look across the void. These are hard testable numbers. And here's the absolute best part. This isn't science fiction.
we can actually do this. We have the instruments. You can see here that surveys that are either already done or are coming online soon, like Euclid and the LSST, are sensitive enough to find this signal. The data might already be out there, just waiting for someone to look.
This brings us to what makes an idea scientifically powerful. It's not just about being right, it's about being able to be proven wrong. And this framework is not shy about putting its neck on the chopping block. I mean, look at this. The paper lays out exactly how to kill this idea. If we look at the data and that epsilon void signal is 0, the theory is in big trouble. If the sign is negative, meaning voids are somehow attractive, it's dead. If there's no link between the signal and how empty the void is, or if the shape of the signal is wrong, again, you have to throw out the idea. That's the confidence of a good scientific theory. It makes risky predictions. And it all comes back to this one absolutely beautiful perspective-shattering quote. For decades, we've been trying to explain the 90% of the universe that's empty void by inventing things like dark energy. We've assumed the void is the weird part. This paper turns that completely around and says, what if we've got it backwards? Maybe the empty, expanding, repulsive void is the natural, simple baseline state of the universe. And maybe the real mystery, the thing that truly needs an explanation, is us.